Awesome. So welcome everyone to today's TCS Plus talk. For those of you who don't know about TCS Plus, it's an online seminar that's been running for over 10 years. And we're always looking for talk suggestions. So feel free to fill out the Google form on our website. And today we're lucky to have Ryan Williams from MIT, who will tell us about a recent breakthrough in complexity theory. Feel free to unmute yourself to ask questions, and I'll also be monitoring the chat so I can relay them to Ryan. So Ryan, take it away.
Great. Thank you. Thanks for inviting me to give this talk. Um, so the main question of this work is how space efficiently can one simulate time efficient computations? So more formally, suppose you have an algorithm A that uses T of n time. We want to find an algorithm B that's equivalent to A. Maybe it does different operations, but it's equivalent and uses minimal space as a function of T. Ordered T of n space for most computational models is trivial. We would like to know if we can save space beyond this trivial bound of, for every single step, we store a constant amount of memory. So a canonical problem to think about here is the circuit evaluation problem, or the so-called circuit value problem, CVP. And in this problem, you're given the description of a logical circuit, you're given an input, a specific input to evaluate the circuit on, and you just want to know, let's say the circuit's got one output gate, if that output's going to be one or not. So given a circuit C, given an X input, compute the output. So on circuits of size S, we can expect it takes about S time to solve the circuit value problem in most interesting computational models that, robust ones that we want to know limitations on. And one intuition is that this probably needs omega S space to store the intermediate gate values, because I didn't put any sort of restrictions on the connections between the gates. So, there could be many, many cuts in this graph between the input and the output, which need S over 10 wires. And so the naive way of solving this thing by dynamic programming would apparently need omega S space to sort of keep track of everything you're doing in order to get the output. But it follows already from the work of Patterson and Valiant, which actually predates earlier, where it's the first paper in this kind of line of work, and borrowed in simulation of low-depth circuits with low space, that CVP actually can be solved in order S over log S space. You can shave a log factor of the space bound. And Hopcroft, Paul Valiant, and others generalizing to other models showed that any problem solvable in time t can be simulated by a different algorithm that uses space ordered t over log t. And just at a really high level, what's going on there is some kind of pebbling approach, which I will talk about later, but there is a hard limitation on what that approach can do. There is an omega t over log t lower bound. So we've known for many, many years how to shave a log t factor, and have some more space efficient simulation. The running time blows up, but the space is less. But we also know that the approaches that have been used to solve this problem could not save even a little bit more than log t. So it was believed that sort of this log t factor can be done, but it's maybe a little trick, and you couldn't do much more than that. So the main model of computation we're going to be looking at here is the multi-tape Turing machine. So I'm going to review that because it's not necessarily something popular in TCS nowadays. So here we have the normal finite control of a Turing machine, but there are multiple tapes, like a constant number of tapes. Let's say there's K of them. The input arrives on tape 1, and everything else starts as blank. And the main idea with the multi-tape Turing machine is you can read and write K cells in each step, one from each of the tapes. And there's K tape heads that can move left or right in each step, and they can move in different directions. The transition function could tell us, that one tape is going to the right while the other is going to the left, and all that. Okay, but we're reading a constant amount of information. We're writing a constant amount of information. We're changing our state. We're moving constant number of tape heads around. Okay, and so we're going to define time t to be the problem solvable in order t of n time on a multi-tape Turing machine. This is the original definition Hartmanis and Stearns. So this is a very old model, but it's very robust. Okay, so just to give some examples, the circuit value problem, sorting, fast Fourier transform, these are all solvable in nearly linear time on a multi-tape Turing machine. So like normally we think about random access models, you can do these on multi-tape Turing machines. All of the known subcubic time matrix algorithms, Strawson and beyond, they can be solved in the same subcubic time with polylog overhead and so on. In fact, just having two tapes suffices. This is a result of Henny and Stearns that given a K-tape machine, you can get a two-tape machine that just blows up the running time by like a log factor in the running time. In fact, like despite 60 years of research, there's been essentially no significant time lower bounds for the multi-tape model other than those obtained by the time hierarchy theorem and things like that. So an open problem is to find any problem solvable in linear time on a random access machine that cannot be solved in n times polylog n time on the multi-tape Turing machine. Okay, so as far as we know, the multi-tape model is as powerful as any other model with respect to time-bounded computation up to polylog factors. Okay, so it's a very powerful model. It's not at all like, say the one-tape model where quadratic lower bounds and stuff like that have been known for many decades. This is a very powerful model. It implements many algorithms that we know. So that makes the main result of this talk all the more shocking, at least to me. Okay, so we can show that for all time functions, which are at least linear, so they're at least n, time t is in space square root of t log t in the multi-tape model. So every multi-tape Turing machine running in time t has an equivalent one using only roughly a square root amount of space. So it's hard for me to properly convey how deeply disturbing this result is to me. So I ignored the basic ideas in this result for months because I thought there is no way that it's true. I hid it from my students to keep from poisoning their minds because I thought I'd kind of lost my mind. I mean, it's a good thing I'm not a gambler because I've definitely bet against this algorithm, which is wild because I'm supposed to be the lower bound skeptic. I'm supposed to be the guy that says, oh, maybe P equals NP, maybe Seth is false, and everybody laughs. So I actually thought that like this is no way something like this is true. So in fact, like I conjectured, and pretty much everybody I knew conjectured that for every epsilon, time t is not in space t to the 1 minus epsilon. Okay, so it's not t to the 0.99. Okay, and people use this kind of conjecture in practice. So, like for example, one of the major early works in de-randomization show that this conjecture, implied with explicit expander constructions, which were later constructed, would imply P equals RP. Okay. This conjecture is now false by this theorem. But nowadays, we know, thanks to lots of later work on pseudorandom generators, that we only need circuit lower bounds on time in order to get de-randomization. We don't need space lower bounds on time, which is actually more powerful if you think about it. So we only need sort of circuit lower bounds on time now. So, okay, I'm not like refuting, all these de-randomization hypotheses. I'm refuting an old one, all right? But it is still something that people largely believe was true. But so like as a corollary, the circuit value problem, now like on a circuit of size S, you can just use square root of S space somehow, reuse space over and over and over and evaluate any circuit you want. Essentially any dynamic program that you set up with like the right structure that like each cell in your DP depends on a constant number of cells that you earlier computed. Now you get a square root amount of space. You don't have to store like big intermediate parts. Another corollary is that size S circuits have branching programs of size only to the O tilde square root of S. So a branching program is basically a decision tree where you get to reuse nodes. So like it's like a DAG, a decision DAG. And this basically follows because we can take a CVP, we can simulate it in small space and then simulate the small space thing using a branching program. Okay, so this is some non-uniform version of the result. Another corollary is that we get we get lower bounds against multi-tape Turing machines. Now, these kinds of corollaries we expect. We expected these corollaries to be true. So for all nice, so time, like say space constructible functions S of n, space S is not in time S squared over log squared. Okay, so like linear space needs essentially quadratic time on a multi-tape Turing machine. So this is a sort of a first result of this kind. But let me emphasize, we expected this sort of theorem to be true. We expect P zoom from P space. We expect the time to go up by an arbitrary polynomial. But the weird thing is the way that it's proved. Like we did not expect that. This is sort of the last way I would ever expect one would prove this theorem, was by showing that you can simulate time t in square root t space. And you can even show there's an explicit there are explicit problems in linear space which are not in essentially quadratic time. Does it mean that something like connectivity cannot be solved in time better than order log squared n? I am not sure about that. I am not sure about sublinear time bounds and distributed computation. I would have to, you have to think very carefully about that, I think. But it's a good question. It's a good question. Perhaps these techniques could be used to show something. I don't know. It's a good question. So one question is like, okay, now we got square root of t space. Like, could we go further? Can we get cube root? Can we get fourth root? Well, I mean, one thing to note that if we could simulate time t in space t to the epsilon for all epsilon, then we will have separated p from p space. But we will have done it in the most surprising way I could possibly imagine, by showing that, like, say, the circuit value problem can be solved into the epsilon space for all epsilon. There is reason to believe from the way the thing is proved that you could possibly recurse, and the paper elaborates on that there is a possibility of recursion, which I don't think I have time to get to in the talk, but we could talk about it at the end. Can I also show that RAM time t is contained in space square root of t? That's a great question. It is still open, okay? I will try to give a high-level idea, like give so many high-level ideas about why I think this can be generalized to random access machines, but we haven't figured this out yet. Okay, it's a great question. It's a great question. Okay, so let me talk about how prior worked. Did their log t savings, because this is important. We'll use some of the conceptual tools that they came up with to get our result. Okay, so the basic idea was to say, okay, I want to simulate a time t computation. I'm going to divide the computation up into blocks. Okay, so I'll divide the tapes up into blocks, and I'll divide the time into intervals. Okay, so given some multi-tape M, given input X, I'm going to partition the K tapes of M into blocks of B cells, where B is some parameter. So let's say that I set B to about the input length. So the entire input fits into a block, and I'm just dividing my tape up into these blocks, and they're all of length B. For simplicity, here I'm just going to think of the time as at least n squared, so I don't think about like having to split the input into blocks, and the block length is about square root of the time. Okay, so let's say I've partitioned my tape into these blocks conceptually, and now I'm going to define a computation graph based on these blocks. Okay, so this graph is a function of the machine M and the input X. Okay, so I'm going to have nodes numbered 0, 1 through Tn over B. Okay, and each node will represent a time interval, represent B steps of time. So the 0th node is just going to be the initial configuration. It's just going to be like some reference point to start with. Node 1 is going to represent the first B steps. Node 2 is going to represent the second B steps, all the way up to Tn over B, which will represent the last B steps. Okay. And roughly speaking, what are our edges going to look like? Well, we want to sort of talk about how the past in the computation is needed to compute the present. So let's say I'm at like a node J. I'm going to put an edge from I to J, where I is less than J, if the information that I computed in time interval I is needed to compute the info in interval J. Okay, so let's say I write to some particular blocks during interval I, and I only visit them again in interval J. Well, then I need the information that I computed in interval I, for example. So to be more formal, the edges we're going to have are for all the relevant I, I'm going to have an edge from I minus one to I. So the idea is that I need the state that I reached in interval I minus one at the end to start up interval I, right? I need the state of the machine in order to start running for like the time interval I plus one. Okay. So I need like what the state was at the end of time interval I. Okay. So I'm going to have like those edges, like sort of a little chain from 0, 1 up to T over B. But I'll also have edges that have to do with reads and writes in the Turing machine. So for I less than J, I'm going to have an edge from I to J. If there's some tape block that's visited in intervals I and visited intervals J, but is not visited in intervals I plus 1 through J minus 1. So it's like your little tape head. Let's see. Can you see my pointer?
Yes, we can.
You can see my arrow. Yeah, so it's like my little tape head, like an interval I, like it runs here. It escapes like in the intervals I plus 1 to J minus 1, let's say over here, but then in interval J, it comes back. Okay. Then I need to know, like, okay, what's the content of this tape block when I'm running interval J, right? In order to, so I need to know what was happening in interval I. Right? So I'm going to have edges capturing that. All right. Okay, so an important observation is in the multi-tape setting, during an interval, each tape has at most 2 blocks accessed. The reason for this is that I set my block length to be B, and I set my time interval length to be B. So if I'm running, for some B steps, then I can cover at most 2 different tape blocks, which are of length B. Right. So if I'm running for B steps, I could run at most B cells to the left, B cells to the right. So I'll overlap at most 2 of these blocks, which are of length B. All right. So each tape has at most 2 blocks accessed during some time interval. Okay. So from this, we can conclude that the end degree of any node is at most 2k plus 1. So we have one edge coming in from node I minus 1 coming from the state. And we have at most 2k coming in. So there's k tapes, and we have at most 2 edges coming in from each of those tapes. Saying like that, right? I need to know like all of these different blocks of information in order to compute what's going on. Because I mean, it could be in principle that I visit these 2 blocks and I don't visit them again until interval I, and I have a separate set of 2 blocks for each of the tapes. Okay. So the main point is that this end degree is constant because k is a constant. All right. So this is important for us. So this is some DAG that we're defining on T over B plus 1 nodes, and it has constant end degree. All right. Okay, so this is just summarizing what the computation graph is. And you see that I have kind of defined the computation graph in such a way that you could imagine it being defined for a random access machine. You can imagine it being defined for any computational model. It just so happens there's some technical difficulties in trying to understand like how to use computation graphs in like the way we're using them for random access machines. But you can define a computation graph for like any computational model, really. So like you can set B to be kind of any parameter you want, and it still makes sense. Okay, so for this computation graph, we have these T over B plus 1 nodes. So we're going to define strings with information computed at each interval. So we're going to define like what is being like, what is the output of each interval? Like, what is the work being done? Okay. So content 0 will just be the initial configuration of M on X, which we can encode in order n bits. It's like in the initial state, reading the first symbol of X, we have X, and then we have blanks. The integrity seems pretty fundamentally unbounded for random access machines. Why is intuition for it end up less than B? Here, so the point is it actually could be B. You could set your block length to be even smaller, and this is actually not necessarily a problem. So yes, it could be B. The integrity could be B. That's actually not an impediment to getting a better space bounded simulation. In fact, because you could set B to be quite small. I don't have time to explain it right now, but yeah, that the constant integrity is definitely particular to Turing machine models. And in fact, in the paper, I generalized to d-dimensional tapes. We have 2-dimensional, 3-dimensional, and so on. But for RAMs, you could actually have a computation graph, even with n degree at most B, and you could still get it, in principle, a space-bound simulation. So good question, though. So content 0, so the first node is the initial configuration. That's the string being computed. It's the information being computed in interval 0. And content I, for I greater than 0, is just the information computed during interval I, which we encode in order B bits. Now, this will be the state and the head positions of the Turing machine at the end of that interval, and as well as all the tape blocks accessed, like all the contents of all the tape blocks we access, which we know is a constant number. Okay, so that will be order B bits for us. Okay, so here's an observation. It sort of follows from the definition of the computation graph, but it's important. So if I give you content of I for all I that have an edge to some j, so if I give you those strings, then you can compute content j. And you can do so in order B time. Why? Because I've given you all the information that you need to compute content j. So because that's the definition of the graph. Like if I give you all the information you need to simulate the Turing machine for B steps, you can do so in order B steps. That's it. Right? So it just consists of simulating the Turing machine for B steps, which we can do in order B steps, given the contents of all the blocks we need and the state and the head positions. Okay. Right. So our goal then is to determine the content of the last node. Okay, the content of Tn over B, because that will contain the accept reject state. So that will just tell us if the thing accepts or rejects, because it gives us the state at the end of the time interval. Okay, so this is what we want to do. All right, so this computation graph is something that people work with, and they were trying to understand sort of how could we get space efficient simulations by thinking about these graphs. So now we have a problem on DAGs. Okay, we have some DAG with a little chain from 0 to 1, 1 to 2, and some other longer edges for reads and writes. And the way it was, the prior work dealt with trying to simulate time t in less space was a model, something they called a pebble game. And it's played on a V node graph, but it's a DAG. And the idea is that we can put a pebble on the source. Okay, that's like saying I can compute the initial configuration anytime I want. So pebbling basically corresponds to computing a content function. And then the second rule is given pebbles on all the I where I has an edge to j, okay, I can put a pebble on j. So if I have pebbles on all the predecessors of j, then I can pebble j. This is exactly like given content, given all these content strings for the predecessors of j, I can compute content j. All right. And I can remove pebbles at any time. And please remove as many pebbles as you possibly can at any time, because the number of pebbles that you have on a graph at any point in time is how much space you're using. It's related to how much space you're using. So the main question in these sort of pebble games trying to get a space-bound simulation is how many pebbles are needed to put a pebble on the last node, right? This is just like trying to determine the content of the last node, okay? And it is known, and it's been proven various ways that actually for DAGs of constant n degree, you need V over log V. Okay. And you can get that, and it is required for many different types of DAGs. Okay. So this was very well known. And in fact, like the upper bound has a computable strategy, like a space efficiently computable strategy. So then, given that you can sort of space efficiently figure out like where to pebble next, given any particular configuration of pebbles, like some pebbles on some nodes, some, like in other nodes unpebbled. So you could just carry out this pebbling that only stores V over log V pebbles at any point in time. So then you would only be storing order T over B divided by log T over B content strings at any time, because our graph has about T over B nodes. Okay, but each content string is order B bits. So this translates to order T divided by log T over B space. So if you set B to be square root of T, or even T to the epsilon for some small epsilon, this will be order T over log T. Okay. So this is sort of how prior work went, but you can see there's like a hard limit on this kind of pebbling. So some important point here is that it is somewhat restricted, because we're only computing content strings onto blank space. So like we're only like taking like content strings that we know and recording them to some fresh space. And then otherwise we're clearing up fresh space. So the difference in this new simulation is that we are not always like making new space and clearing up space. We're actually going to like take content strings and sum them on top of each other many, many times. Do some weird XOR tricks. Okay. So like this new simulation sort of highlights what the limitations of this Pebble game were. Okay. So how do we go towards low space? It starts with this problem called tree evaluation. Okay. And this was originally defined and studied by Braverman, Cook, McKenzie, Santanam, and Ware in 2009. And there are several parameters, several moving parts. So I'll try to go slowly here. So there's a parameter D, B, and H. I mean, often D is just set to be 2. So you're given, let's say, a binary tree of height H. And each inner node is labeled by some function, okay, which takes dB bits and outputs B bits. Okay, so each function is given as a table of length 2 to the dB. Okay, so let's think of it this way. So we've got like the root node is labeled sort of epsilon at height 1, and then there's D children. Each of those are labeled 1 through D, and there's a function for that. And so each of the inner nodes will be labeled with some function, and this is some D-ary tree. And then down at height H, we have leaves. Okay, we have D to the H leaves. And each leaf will be labeled by a value, a B-bit value. So for leaf L, it will be A sub L. Okay, so we have B-bit values of the leaves. We have these sort of functions given to us by tables for each of the inner nodes. All right. Now, for an inner node U, if I have values for its children, then the value of that node is just the result of applying the function on that node to the children. Okay, so like I just apply f of u to the children, and I get the value of that node. Right, so you can imagine starting at the leaves, evaluating everything at height h minus 1 using those functions, h minus 2, all the way up to the root. And then the goal of the problem is to find the value of the root. Okay, find what you get at the end from this evaluation. Okay, note that if b equals 1, this is basically Boolean formula evaluation, right? So if b equals 1, I have like 0, 1 is at the leaves, and I'm just evaluating some functions that take 2 bits and output a bit, right? So, but here I'm taking functions that take, say, 2 b bits or d times b bits if it's d-ary, and output a b-bit string. Okay, so it's just a generalization of Boolean formula evaluation where you allow for functions that take b-bit values and output b-bit values. Okay, So there's a simple recursive algorithm for finding the root. So the idea is that at any particular node, if it's a leaf, then we can just look it up, right? We're given the values of the leaves, okay? Otherwise, for each of the children of our current node, we can compute recursively tree evaluation on that node, okay? Once we've got the values of all the children, we can evaluate our function by looking it up in this table and then erase those values. Erase those values because we don't need them anymore, okay? All right, so if you think about like different ways you might implement this recursive algorithm, you could do it in a depth first way, right? Where you have a stack of height h, and at every level of your stack, you're storing about order dB bits. Okay, you're storing like sort of intermediate children values you've got so far, but you're still trying to find some like some other children values. Okay, so a naive sort of depth first implementation of this will take h times d times b space. Okay, and so if our input length is capital N, so I told you the values of all these leaves, I've told you all these functions, this is about order log squared capital N for the input length. Okay. So we'd like to know sort of how much space does this really take? And the main conjecture that Braverman et al. Had was that actually this algorithm should be optimal. It should take about log squared in space, and there shouldn't be something better. And they showed lower bounds in lots of restricted settings. In fact, they conjectured this tree evaluation problem is not even in non-deterministic log space. So like even with non-determinism, you couldn't do much better. Okay. Okay. So it was a big surprise when Cook and Mertz last year showed that in fact you can simulate tree evaluation in essentially log n times log n space. So for us, we can do tree evaluation in order the height times log of dB plus dB space. Okay. Remember the thing we're trying to be is h times d times b, right? So, and if d is constant, this is sort of like saying we had h times b space before, and now we have almost h plus b space now. Okay. So it's a big space savings. And their algorithm uses a stack of height h with only log of order dB bits on each level. Okay, so like the things being stored at the stack is much less, and we're aggressively reusing order dB bits of space at every single level of recursion. Yeah, I mean, essentially, this was quite surprising. And the goal of my talk in this paper is to give a surprise preserving reduction from, simulating time with space to this tree evaluation thing. So use the surprise of this to find another surprise. Okay. Let me say at a really high level how their algorithm works. So the simple algorithm that I just outlined, it allocates fresh space for every value you compute at each level. So you're never writing to something that's right there. You're always sort of imagine you can write to blanks. Okay. So, there's this like old trick of if I've got two registers and I allow myself a third empty register, I can swap the values of the two registers, right? Using fresh space with a third register. I could also do 3 XORs cleverly and not use a third register. By sort of XORing content, of registers into each other, I can actually swap them. Okay, so imagine that on steroids and mushrooms and everything, and that's kind of what's happening here. Like instead of instead of having like fresh space for things, I'm actually XORing lots of things over and over and over into the same registers. Okay. So we're going to XOR values into existing space. Their algorithm XORs the value of a given inner node into existing space, assuming you've got an oracle that can XOR the values of the children into existing space. Okay. And the idea is that you're going to basically work with the low degree extension of these functions, f, treat them as polynomials, and you'll be doing some running sum to try to align your XORs so that no matter what content you started with an existing space, that will be canceled out, and you will get the value of exactly the value of the function on the children. Okay, so we're at a really high level. We consider the low degree extension of each of these functions, which can be evaluated in order V space. And we use polynomial interpolation tricks on the existing space to XOR the value of this thing into existing space into some other register. I mean, that's about as much as I can say here and still stay within time. Okay, but this is the high level idea. This is the major change between the obvious recursive algorithm and these pebbling arguments to evaluate computation graphs. Okay, so let me talk about how you can simulate time t in space square root of t with a log t factor. So this is a little bit weaker than what we had before. The idea is given a time t multi-tape Turing machine at input x, we want to reduce to an exponential size tree evaluation instance. We will not hold that entire thing in memory. We will be able to compute sort of where we are in the tree and what the children are and what the values of the leaves are at any point. Okay, so we can access this thing with low space, and we're just going to apply Cook Mertz to it. Okay, so we start by assuming we know the computation graph. Okay, so either it's stored in memory or we can somehow compute its edges efficiently. All right, so we'll set our d, like the arity of our tree, to be 2k plus 1, because this is the n degree of our computation DAG. We'll set the height to be the number of nodes in our computation graph, which is 1 plus t over b. And we'll set b so that for all I, the content, each content string has length at most b. So maybe adjusting by some constant, to get that to work. And then we need to extend this Cook Mertz algorithm so it will work for trees that have at most d children in each node, because we just said the n degree was at most 2k plus 1 and max height h. So it could be you reach a leaf earlier. So it could be like a irregularly shaped tree. We just want the algorithm to work there, and it's pretty easy to generalize it so that these things can happen. Okay, so now we use a sort of folklore result, which is pretty simple. We start with the observation that if you have a Boolean circuit of depth h, you can translate this into a Boolean formula of depth h, so it's like a tree-like circuit. Okay, so just to give you a little picture, suppose I have a Boolean circuit, so I'm computing 0, 1 values at each node. I want to get a formula. Well, I start from the output node, okay, and then just sort of work my way back. Right, so the nodes going into the green node are blue and yellow, right? And if I look at the blue node, well, there's red going into that. And if I look at the yellow node, well, there's red going to that, there's blue going to that, and there's red going into that. So you can imagine just unrolling the evaluation of the circuit starting from the output gate, and you'll get a tree-like formula. Now, the formula is much larger in principle than the circuit, but it will be a formula of depth h instead of the circuit. One intuition here is that each gate of our formula is going to be indexed by a path from a gate in the circuit to the output gate, right? So they're sort of going over the possible paths to the output gate, all right? Now, the observation here is that this transformation works just as well for circuits and formulas with b-bit values on the wires. Okay, so it's, this is a folklore result about Boolean circuits, but it works just as well if you have b-bit values on your wires. Okay, so if you're passing b-bit values around, you can still enroll it just the same. And okay, but what does it mean to compute a content string in this computation graph? This is evaluating a circuit over b-bit values, right? We had these content strings, we had these edges telling us how things relate, and then given these content strings, I can compute this content string if I have all of the predecessors. This is just evaluating a circuit over b-bit values, okay? But okay, once I have a tree, once I have a Boolean formula, the tree evaluation problem is nothing more than evaluating a formula over b-bit values, where the formula has depth h and has fan-in d. Okay, this and I gave you the values of all the leaves. Okay, all right. So as long as I can do this transformation of circuits into formulas in a space efficient way, and then I can call tree evaluation, then I can reduce this simulation of the computation graph to tree evaluation. Okay. So the idea is that we can evaluate the content of the last node of the computation graph, determining accept or reject using the Cook Mertz procedure. But the space of Cook Mertz, sort of plugging in the parameters, is order b plus t log b divided by b. Okay, so setting b to minimize these two, we get about square root of t log t space. Ooh, but we don't know the computation graph. We assume that we know it. We assume we could access it however we want. Okay, so the easiest fix to this is to just program the Turing machine so that we can calculate all the head positions quickly in advance. So that way we can actually determine the edges of this computation graph efficiently. So to this end, we say a machine is oblivious if for every n, for every x of length n, the head movements of m only depend on n. Okay. Then there's a theorem that says for all multi-tape Turing machines in t of n time, there's an equivalent two-tape oblivious one that runs in t log t time. And then moreover, if I give you n and I in binary, I can compute where the head positions of this new machine will be at step I very efficiently in polylog n, polylog t time, and polylog t space. Okay, so using this, I can really quickly look up any edge of the computation graph I want. Okay, so then we can compute this graph on this m prime, but we lose a little bit because we have a log factor there. Okay. Okay, so how do we get the final theorem, which has square root of t log t? And this reduction is going to have the property that actually, if this tree evaluation problem turns out to be fully in log space, not just log n times log log, then we would get a clean simulation of time t in space order square root of t. Okay, so the high level idea, what do you do when you have, there's this thing called a computation graph, but you just don't know how to get it? What do you do? Well, you guess it and you check it. Okay, that's what you do, right? It's the basic non-determinism thing. Okay, so the observation is that we can actually encode this computation graph very efficiently. So it's got t over b plus 1 nodes. You can actually encode it, no matter how its edges are, in order t over b bits. And this uses properties of the Turing machine. So for each tape and for each interval, we can use a constant number of bits to indicate sort of which tape blocks adjacent to the one containing the head are accessed in interval I. So like at any particular point, we're at our tape head is in some tape block. And in an interval, we could only access the one to the left and the current one we're in, or the one to the right and the current one we're in, or just the one we're in, right? So that could be encoded by saying 1, -1, 0, 0, or 0, 1. And so this is just a constant number of possible choices, okay? Then we also want to say how the tape block containing the head changes from interval I-1 to interval I. So, and this is just some number saying either you subtract the tape block index you're in or keep it the same or add 1 to it. Okay, it's only changing by 1. And then we can check if there's an edge from I to j by keeping counters for each tape that store the tape block index, assuming this encoding. So given this encoding, we can recover what the computation graph should look like, okay? So there's a very succinct way to encode this graph. Now, given it, right, it could just be wrong. It could just be claiming you access some tape block when you don't, or it could be leaving out some tape block that gets access. We got to check it, okay? The main point is that by keeping these counters around, it takes only order log b space to determine any edge in this graph, just by storing counters and going through this encoding. So to check it, we're given some encoding of a graph, and we want to check that it's equal to the right graph, okay? So this encoding is going to assert exactly which tape blocks are accessed during interval I, okay? And we want to make sure it's honest, and it's always accessing exactly the correct set. So we'll define our tree evaluation function on all the nodes so that its behavior depends on the computation graph, okay? So when I'm simulating m in some interval I, if a tape head violates G prime, so if it accesses something it's not supposed to, or if it doesn't access everything it was supposed to, then my function will output a special fail value. And if any input is fail, it just immediately outputs fail. So if there's any point at which it's violating what the graph encoding said, it will say fail at the top. So the resulting tree evaluation just doesn't output fail if and only if the graph I've got is correct. So I just run through all the graphs, all the possible graphs, and I make a special tree evaluation problem for each one, and it will either output fail or give me the correct accept reject decision. Okay. All right. So that's the idea. All right. So let me end with some open problems. So as already asked in the chat, could we extend this to random access machines? Can we show that time t on a RAM is in space t to the 1 minus epsilon? Could we extend to parallel machines? So I interpret this as, can we show that time t is an alternating time t to the 1 minus epsilon? So this would actually imply a superlinear time lower balance for problems like quantified Boolean formulas. So I think the first step is to just improve the 1/2 exponent. So actually, you can show that if you could improve the 1/2 to half minus epsilon for some epsilon, this would already resolve the first two problems. So you'd already get a RAM simulation from this. Another question is, okay, assume P equals PSPACE. Can we then prove P is different from PSPACE? Can we then simulate time T in space to the epsilon? Okay. Another question is whether there's a barrier here. And I think that we should just not talk about barriers right now. This entire thing is super disturbing to me. Like if I had thought about tree evaluation like 2 years earlier, before Cook Mertz, I would have declared this result to be a barrier. It would have not been a very big deal. I would have just said something like, look, you can't solve tree evaluation in much less space, or you'd improve this like 50-year-old simulation, which we know we can't do because why, right? So I think complexity theorists should stop intimidating each other from working on problems. So let's not talk about barriers, okay? Let's just try to find algorithms, okay? Okay, that's all. Thank you.
Thanks, Ryan. I'm going to stop the recording and then we can take questions offline.
Sure.